So welcome everybody to round 2 of the Algebra Particles and Quantum Theory Seminar Series. I'm very grateful to be able to introduce you to tonight's speaker, Sir Roger Penrose. Sir Penrose is the Emeritus Rose Ball Professor of Mathematics at the University of Oxford. And whether it be directly via his scientific results or via the communication of his unusually original ideas, Sir Penrose is easily one of the world's most influential mathematical physicists. His inquiries into mathematical physics have set in motion the cosmic censorship hypotheses, the Weyl curvature hypothesis, Penrose diagrams, spin networks, Twistor theory, conformal cyclic cosmology, the Penrose interpretation of quantum mechanics, Penrose tilings, and the Penrose triangle, just to name a few. He influenced by some of the most striking works of the visual artist M.C. Escher. Sir Penrose has even ventured into what was once a forbidden forest through his interrogation of the nature of consciousness. Professor Penrose has authored a number of popular books, including The Emperor's New Mind, Shadows of the Mind, The Road to Reality, Cycles of Time, Fashion, Faith, and Fantasy, and the New Physics of the Universe. Appreciation for his contributions has been reflected via a multitude of awards. This includes the jointly won 1988 Wolf Prize in Physics for the Penrose-Hawking singularity theorems. It includes being knighted in 1994 by Queen Elizabeth for his service to science. It includes jointly winning the Nobel Prize in Physics just 2.5 years ago for the discovery that black hole formation is a robust prediction of general relativity. Sir Penrose's work is consistently visual, creative, sophisticated, and fearless. Although perhaps seemingly wild at times, it largely keeps its sights firmly fixed on the real world in which we inhabit. Even from the outside, it is obvious to many of us that Roger Penrose has been unapologetically searching for it. Now, before we begin, today's crowd is a little bit larger than usual, so it would be helpful if people could please ask only clarification questions during the talk, and then, of course, it will be fair game to ask more expansive questions after Professor Penrose's talk. So thank you so much, Professor Penrose, for agreeing to give a talk for our series. Anytime you're ready.
Okay, well, thanks for the introduction. Can I start now?
Yes.
So here we have the title, and I think I better move on. Anyway, it's about Twistor theory from its origins. So I'm going to compress a lot of work in my talk, I'm afraid. I hope that's okay. I'll do my best. Which one is it? The middle one or the bottom one? It's the third one. It's not working. Oh. That's it. Now it's working. Thank you. All right. Yes. The sort of origin of Twistor theory really occurred when I was in Syracuse, this was in when was it? 1961, 60. And I occupied an office jointly with Engelbert Schucking, who was a very original and knowledgeable person, both original and knowledgeable, which is unusual. And he told me two things which were very important to me. One was that Maxwell's equations were conformally invariant, so that they don't actually depend on the complete metric, but just on the metric up to a scale. We'll come to conformal ideas shortly. Conformal invariance. And the other thing he told me about was that in quantum field theory, one of the important things about quantum field theory is that you have to be able to take the positive frequency terms. You split your field quantities into positive and negative frequencies, and then you take the positive frequencies for quantum field theory. Now, the thing is, I was a little worried about this, because usually when you take positive frequency, that means you take the Fourier components and you take the positive frequency ones. But the Fourier components are not conformally invariant. So if you're thinking about Maxwell theory, you have to do something which is conformally invariant. If the quantum field theory is at least to follow the classical theory in that respect. So I thought of a different way of looking at splitting positive and negative frequency. I guess it's well known, but this was the way of doing it. I imagine here that you have the Riemann sphere, so that's the complex numbers together with infinity folded up into a sphere. And I'm looking at the equator as being the real numbers. And you consider functions on the equator. And if you orient things the right way around, positive frequency will extend into the northern hemisphere, and the negative frequency ones will extend into the southern hemisphere. So you don't need to do the Fourier decomposition. You just look at the whether it extends one way or the other. And I rather like that idea. And I was trying to think of whether one could extend that to a global picture of space-time. So that in some sense, I would replace this picture by space-time in some way. But the trouble with that is, if you think of the real space-time and you complexify it, it doesn't work, because the real space-time is 4-dimensional and the complexification is 8-dimensional. So the 8-dimensional space does not divide into two in this way. So how do you do it? So I puzzled about this for a long time, and it didn't seem to me, so maybe a crazy idea that doesn't have any, is it the middle one or the side ones?
The side ones.
Okay, yes, here we go. So I eventually came across this picture. So rather than thinking of space-time in the ordinary way, I think of light rays as the fundamental things. And so here we have a light ray, that's a null straight line in space, in Minkowski space. And that is represented by a point. And if you want to represent a point in space-time, you think of the sphere of light rays through that point, which is a nice complex thing. It's a Riemann sphere, if you look at it the right way. And this is the picture that seemed to do what I wanted, because you can think of, which one? I've forgotten. The middle one or the side one?
No, not the middle one.
It's the side ones. Okay, here we go. I'm just trying to remember that. Sorry. Sorry about all that. Yes. The picture is basically this, that you can think of the light rays as being sort of particles which travel at the speed of light, but they don't have any helicity. They don't spin about their axis like a photon does. And then you can spin right-handed or left-handed, and it turns out this only adds one dimension to the space-time. On the picture I have on the right here, and try and represent this, is what I call PT, and PT plus and PT minus. What's that mean? Well, T is actually the Twistor space, which is a 4-dimensional complex vector space, and the P means projective. So this is a projective, you're just looking at the ratios, the complex ratios, and that's then 3 complex dimensions, so 6 real dimensions. And the space of light rays is 5 real dimensions, and that does divide it into 2 halves. So it does that sort of funny thing. So that was really what I was concentrating on. And what do you represent? Well, you see, this picture is why Twistor theory is called Twistor theory, because this is a way of representing the photons in the top and the spinning photons. I'll come to why that does in a minute. This is a configuration which I was familiar with at the time. It's the Clifford parallels. You take a 3-dimensional space, a 3-dimensional sphere, and you can fill it with circles. And these circles twist around each other and link, every 2 of the circles link. And this is what's called the family of Clifford parallels. It's what people call the Hopf map. Hopf knew about Clifford parallels, and he used that in his understanding of these vibrations. Now, where does that come into the picture? Well, here is the picture again of what I had before. The Twistor space, that's T, and the projective Twistor space, that's PT, and it divides into 2 halves, depending upon whether a quadratic form is a positive or negative, or it's a Hermitian form. And the top half is when it's positive, and the bottom half is when it's negative. And you also have a duality notion in this projective space. So a point in Twistor space will be associated with its dual, which would be a plane, complex plane. So this is a 4 real dimensional space, 2 complex dimensional space. And the point up on the left hand, that's called Z alpha. And the complex conjugate of that is meant to be, is also a dual. So when I put the index down, that means it's a dual object. And the complex conjugate in this way of doing things is actually a dual object. And that plane intersects PN. Well, PN is where the light rays are in what it turns out to be a three-sphere. So you see S3 marking the intersection of that plane with the light ray space. So you have a family of light rays, and that is the family which twists around in the complicated way I showed you. Now, where are the circles? Well, you think of a line through the point Z alpha on the top left in the picture. That line is represented as a sort of sausage, because a line really is a sphere, because it's a complex line. It's a Riemann sphere. And that sphere intersects the PN space in a circle. And as you move it around, intersecting that intersection, it produces this configuration of circles, the one that I showed you. And it is the Clifford-Hopf vibration, which I have on the bottom right of the picture here. So that's what it's doing. Okay. Now, to understand these things, it's really best to describe everything in terms of two spinners. So if you're not familiar with these things, it's a bit of a nuisance, but I'll give you a rough idea. Geometrically, what a two-spinner looks like, well, it's really on the right-hand side of this picture. It has a flagpole, which is a null vector, and it has a flag plane, which is a little two-plane through that null vector. And on the left-hand side, you can see what the direction of that flagpole represents a point on the celestial sphere. Well, this is the time-reverse celestial sphere, if you like. That sphere, which is marked as S plus, I think, in the picture, that is it's represented on the right-hand side as though it looks like a circle angled at you, but it's actually a sphere because of another dimension. And the sphere is represented on the left-hand side. That is the celestial sphere, well, this future celestial sphere, if you like. And the flagpole represented by a single point, and the flag plane is a direction on the sphere through that point. Now, it's a spinor object, so that means as you rotate that flag plane around the flagpole, you have to go twice round before you get to where you started. If you go all the way around through 360 degrees, it gives you minus the spin over the 300, whatever it is, twice 360 degrees all the way around. It gives you back to where you were. Okay, so that's the sort of geometrical representation of a spinor. It's useful to bear that in mind, that these things are very geometrical objects. They have this spinorial characteristic that when you rotate them once all the way around, they become their negatives, but that you have to get used to that. Okay, now what's a twistor? Well, a twistor is represented by a pair of two spinners. I call these omega and pi for reasons which will come shortly. The pi is the direction along the light ray. So you see the light ray I'm calling Z intersects the light cone of the origin, and that point where it intersects it, you join that to the origin, and that's another light ray, and that's the one I call omega. So you have omega and pi, and the two of them together describe a twistor. They describe a light ray in particular case, that's when in the general case, but they also give you the more general case, which you can't represent as a light ray. In fact, the twistor, as you see here, Z alpha, I tend to call the twistor Z, and its index is a Greek letter alpha. The upper alpha represents the direct sum of an upper spinor, two spinor, and a lower primed two spinor. So the unprimed one is the first two components of the Z, and the second two components of the Z correspond to a primed spinor, which is a complex conjugate. So it's not only a dual by having it downstairs instead of upstairs, but it's also a complex conjugate. And the complex conjugate of the twistor is a dual twistor. You have to swap around the two parts. Z alpha now has an index down because it's a dual object, and the pi's and the omega switch round, and the pi now becomes an unprimed lower index thing, which is a dual to the omega at the top, and the omega part is the now has a primed index. Okay. Now, I think I wonder if I shouldn't have gone ahead. Let's do it this way. A lot of things I will be described in two-spinner notation, so I hope you don't mind. The capital letters represent the spinor indices, the primed ones are the complex conjugate ones, and the tensor indices are written with little Roman letters, where the little a really stands for a big A and a big A prime. And a little b stands for a big B and a big B prime. I'm using abstract indices, so don't worry about the components. That comes later if you want to. But that's how I get away with it. The metric is the thing in the middle, G, A, B, lower, and that represents, that's in spinor notation is an epsilon. The epsilons are skew symmetrical, so that you have two epsilons, and that makes the G symmetrical. And the complex conjugate, or the complex conjugates of the epsilons, well, I still write it with an epsilon, but the indices change from being unprimed to primed. Now, if we want to have a Maxwell tensor that splits into two parts, that's convenient because one of them it corresponds to the right-handed helicity and the other to the left-handed helicity. I think it's the primed one is actually the right-handed helicity, and the unprimed one is the left-handed. So you can see that the Maxwell field tensor, which has got two symmetrical indices, and it splits into a symmetrical thing phi and the anti-symmetrical epsilon, and those together give you the anti-symmetry of F, and you add that to its complex conjugate, and you get the anti-self-dual and the self-dual parts, giving you the left-handed and the right-handed spin of the photon. Now, the Weyl curvature, what's really nice about it is when you write the Weyl curvature, that's the conformal curvature, that's the conformal part of the Riemann curvature, and it's all very nice in spinors, and tensors it looks very complicated, but in spinors it's just a symmetrical thing, psi, A, B, C, D, that's the left-handed part, I think, and the psi bar has its indices primed, and that is completely symmetrical. You have two epsilons to make the C have its right symmetries and trace-free properties, and it gives you everything you need. The zero Rass mass field equations, what I like to think of the zero Rass mass field equations, in the case of the Maxwell field, they are the pre-Maxwell field equations, and in the case of the Weyl curvature, the Bianchi identities as applied to the Weyl curvature, and they are just the same kind of equation. You see it at the bottom. You have the symmetrical tensor, symmetrical spinor, and it's covariant derivative, which acquires one primed and one unprimed index from the contravariant index, tensor index, and you just contract one of the indices, and that vanishing is the Bianchi identities in the case of the Einstein field equations, and the free Maxwell equation in the case of the other one. Okay, so these are the massless free fields, which fit very nicely into twistor theory, as I'll explain in a minute. We have the negative helicity ones with the unprimed indices, the primed ones with the positive helicity, and for zero helicity, well, you don't have any indices, so you just the wave equation there. Now, if you want to represent the general solution of these equations, there's a very nice formula in twistor theory, which I'll explain why it's a twistor formula in a minute. That's given in the second from the bottom line. You see the contour integral, where you put I should say that we have the green thing in the middle is the twistor function. The twistor function is a holomorphic function, so it's complex analytic, and it has homogeneous of degree minus 2s minus 2, where s is the helicity. So and this could be s can be an integer or half integer, so minus 2s minus 2 turns out to be an integer. So these things are integer homogeneity functions. And each one of these gives you a general solution of your appropriate equations by doing an appropriate contour integral, where let's take the second from the bottom equation, and I look at the first one of those two. That is, I'm looking at f multiplied by enough pi's to make the homogeneity minus 2, and then I make it up to 0 by putting that differential form, which is the bottom line. That is a differential form which is really made out of the pi parts of the twistor, and the pi's are giving you your indices as needed. The homogeneity of the whole expression comes out to be 0. You have a nice contour integral, and on the right-hand side, you, instead of putting pi's in there, you put d by the omegas. So the d by the omegas each give you a negative homogeneity, and they make it up to 0 again. So that's exactly the integrals you need, and they give you solutions to these equations. Now, I'm not going to go into the details of that, but what I am going to do is to show you where the integral takes place. So this is really the important thing. I have on the left-hand side a picture of the singularities of your twistor function. So the twistor function is organized, so its singularities have a couple of camel humps, if you like, in the northern hemisphere, the northern part of the twistor space, and they can kind of do what they like in the bottom half, but they have to form two separate regions of singularity in the top half. And the reason for that is that if I have a line in the top half representing a point, that's a point in the forward tube, actually. And the thing about that point is that the contour integral is well defined in that, as long as that line lies entirely in the top half. And you then, in the right-hand side, you see how that line, being a Riemann sphere, intersects those two camel humps in two regions of singularity, and your contour just nicely slips around between the two and gives you a nice answer. So as long as the camel humps are separated like this in the top half, you get a nice field. And because this function extends non-singularly into the what's called the forward tube, you get a positive frequency field. So this is a way of not only generating general solutions of the equations, but you automatically get wave functions. These are positive frequency fields, as they should be. And it's sort of doing the kind of thing I was wanting twistor theory to do. Now, it's even more so if you look at these things in the right way. This picture is really the same as the picture I had before, but it's drawn rather differently. Where are the camel humps? Well, the camel humps are the unshaded part of the top half of twistor space. The shaded part is where I'm going to do the contour integral, and that's the same as what I just had above. The contour integral goes round in the dotted part, if you like, and it's just the same as the previous picture. But I'm thinking of it rather differently. I'm thinking of the top half as being the union of two open sets. These two open sets are the left-hand part included the dotted part, or the right-hand part included the dotted part. And you see that the one of the camel humps is absent from the left-handed part, from the left-hand open set, and the other camel hump is removed from the right-handed open set. So you have a region where the intersection of these two open sets, the two open sets, the union of the two open sets gives you the whole of the region you're interested in, whereas the intersection of them is where you're doing your contour integral. Well, this is really a simple case of something more complicated where you could divide the whole fragment into many, many sets. I don't want to do all that because it's really not really I don't have time to describe all these things. It's very beautiful the way it works, but it's not something I can spend time describing. But what I do want to say is what it's really doing is cohomology. And cohomology, if you want to describe what cohomology is, it's the easiest way I can think of describing it is that by an impossible object like this. So this is an object which, if you consider just part of it, let's suppose you divide it into 3 corners, and those 3 corners slightly overlap with each other. So they join together to make the whole impossible triangle. But each of the 3 corners is perfectly possible. So you can imagine a picture which has 3 pictures which are trying to glue together. And those 3 pictures glue together in a way which is inconsistent. It's inconsistent because you've got the freedom in a picture. You don't really know how far away the object you're describing is. It could be closer to you or further away. It gives you the same picture. So on one of the edges, the join is arranged so that you make your picture so that they join up properly, and then you try to do it on the next edge, and then you find you've made a mess of it because the last edge doesn't work. But the thing is, the measure of the impossibility of this picture is an element of the cohomology. So it's a nice way to think of cohomology. But in Twistor theory, the cohomology is really, it's only done with 2 sets here, but you could do it with more sets in general. And the object, the gluing region is the one in the middle, which is how you glue your corners of the impossible triangle together. And that's why I say it's really describing a thing like this, that you have a holomorphic function to tell you how to join your bits of function together. And the impossibility of the function is what you get from the contour integral. So the contour integral is really a measure of that. I'm afraid that's a long story, which I've compressed into a few sentences, but it really does work. And that really what you've done is to describe your zero rest mass fields in Twistor language are first cohomology objects and if it's a wave function, then it's the first cohomology object of the top half of Twistor space. So at last, one actually does realize what it was trying to do. So it took several years, I may say, to get to this picture. And I had to learn a lot of things I didn't know at the time. Cohomology was one of the things which it was nice to share an institute with Michael Attia, who was somebody who could explain these things very well to an ignoramus like me. And it was he told me what I was doing was cohomology, which I hadn't realized before. Okay, so this is the splitting of your cohomological objects, which describe the fields, into the top half and the bottom half. And if you want to talk about positive frequency wave function, you're talking about the top half. So it really did realize this motivation, which I had from way, way back, in a completely unexpected way. Was I just lucky? I have no idea. Anyway, but this is something more to you. So I rather hurriedly made this picture, and it's a bit of a mess. But you see, you can use cohomology in an active way. What I've just been talking about is really cohomology passively. You've painted it onto the space in a certain sense. But you can do it actively, rather in a way that this triangle, you see, you're using your cohomology in an active way to try to construct this impossible object. Well, the same sort of way now, I'm using this actively. Now, this works most clearly in the case of helicity, in the left-handed gravitational fields, because you find that you can then use this Twistor function to describe a displacement of half your Twistor space, top half. The 2 parts here represented 2 parts of the top half of the Twistor space. So I'm covering the top half with 2 open sets. There's 2 sort of blocks in this picture here. But now I'm displacing one with respect to the other. And when I displace it, if it's an infinitesimal displacement, well, then really it's still doing the cohomology as a sort of passive thing. But if I'm regarding it as an active thing, I can here in this picture. And I move one with respect to the other. But now the trouble is, if I had one of these lines which represents a point in the space-time, that's that little sausage which is going from left to right, and it represents a Riemann sphere, which you can see on the right-hand side of this picture, that Riemann sphere will have got broken. So I have to find another one which twists its way through from one side to the other, and you can prove nicely that as long as you haven't moved these things too far apart, you have a 4-parameter family of these things, which gives you a 4-dimensional space, and it gives you a general solution of the anti-self-dual Einstein equations. So it was a great triumph of twistor theory to do this in a very natural way. It's sort of non-linearizing your element of cohomology. The snag about this thing was that it doesn't give you solutions of the Einstein equations that you tend to normally to be interested in, because these are anti-self-dual solutions of the Einstein equations. They're complex solutions for which the self-dual part of the Weyl curvature vanishes. And because in the ordinary signature of space-time with 1 plus and 3 minuses, your self-dual and anti-self-dual parts are complex conjugates. If the self-dual part vanishes, then the anti-self-dual part also vanishes. And so all real solutions, they vanish completely. The mathematicians really liked it because they didn't like that signature. They like positive definite signature. It's not space-time in the ordinary sense, but it gives you a whole nice theory which can be played with in pure mathematics. And in fact, people did. So it formed a nice theory, which Michael Atiyah was one of the founders of. And certainly that's one way of using twistor theory. But it's not twistor theory, it's what I call pseudo-twistor theory. It's twistor theory with the wrong signature. When I say the wrong signature, it's not the signature which gives you a plus, minus, minus, minus space-time. Now, this was the problem which has stuck with us for a long time. It's called the googly problem. For those of you who members of the old British Empire know what I'm talking about, probably, because this is a cricket term. It talks about the cricket ball, which is bowled in a way which looks as though it spins left-handed and actually spins right-handed. So what you want to do is have a version of this construction which enables you to spin it the other way around. And this was a real challenge in twistor theory, which never really found a proper solution. Now, maybe it does find a proper solution in a way which I want to try and proceed. So let me go a little further here. First of all, let me just say a little bit, going back a bit, really, but to say more about twistors and their physical interpretation. Because a twistor really does describe not just a sort of complexified null ray, but it describes angular momentum very nicely. An angular momentum of a massless particle. So here I have the momentum, which is null. At the bottom of the Brown equations, we have the P, which is the momentum. I should say the reason that I chose pi, which is because it's describing P, which is the momentum. The angular momentum is a sort of, the letter omega tends to be used for angular momentum. So that's why I chose the letter omega for the angular momentum. Now you see the total angular momentum involves both the pi and the omega. So you see this expression at the bottom here, which has the symmetric product of the pi with the complex conjugate of the omega and the complex conjugate of the pi with the omega. And then you form the combination of them, which gives you the angular momentum, MAB. But you see that it does really give you that, and it satisfies the conditions that you need for the momentum and the angular momentum of a massless particle. If you construct the spin out of it, the spin is, the spin vector, the Pauli-Lubansky spin vector, points parallel to the momentum, which it automatically does with this description. So it really does fit in nicely with the correct way of thinking about momentum, angular momentum, and momentum of a massless particle. Also, as you change your origin, the omega moves in the way that it does in the descriptions that I've implicitly in what I told you earlier, and the pi remains constant as you move it. But it also has the property that when you go to quantum theory, it behaves correctly with the canonical commutation rules of twistor theory. So these are very naturally things that you do because it fits in with angular momentum. These commutation rules tell you that the z's commute with themselves, the Z bars commute with themselves, but the Zs and the Z bars are canonical conjugates. So you see the top line here, Z bar minus Z bar Z is H cross times the Kronecker delta. It does actually fit in implicitly with what I was saying earlier. I think I can go back to these contour integrals here. But when I had on the left-hand side, right at the bottom, the second line from the bottom, I had a lot of pi's in the integral. When I did the other helicity, I have a lot of d by d omegas. Well, you see the d by d omegas really are the canonical conjugates of the pi's. And it's an appropriate thing when you go to the, what I was doing here, the canonical conjugates between the z's, that really means that z bar looks like d by dz, behaves like d by dz, and z perhaps like d by d, one with a minus sign. So it really fits in with those contour integrals, and it seems to be absolutely the right thing to do with twistors. Okay, now that's fine, and that's been with us for a long time, and it's a very natural thing to have. But what I want to do now is to consider, you see, there was this googly problem which somehow says that we should try and combine the twistors and the dual twistors in a way together. And there's another thing which it sort of says. You see, in what I was talking about, I confused two things without really expressing why I was confusing them. The two things I was confusing, and let's go back to this, sorry, back to here, if you like. Here you see, it does actually do what I was trying to do with a positive frequency of a negative frequency. But if you remember right from the beginning, it represented positive and negative helicity. Well, if I go right to the very beginning, yeah, positive and negative helicity. So I'm trying to do two things at once in twistor theory, which we sort of lived with for a long time. And it seemed like, all right, somehow it'll resolve itself. But what I want to try and do here is not to say that, but to address the problem head on. In other words, I'm going to consider an object, which I'm going to call a bitwistor. The curly A at the top here is a bitwistor. It consists of two parts. One is a twistor, and the other is a dual twistor. But they are multiplied by a canonical conjugate Z's and W's. So the Z's and the W's in bold type, those satisfy the canonical commutation rules above. So those do satisfy these canonical commutation rules. So they're really quantum objects. The A's there are classical objects. They are the coefficients. So the curly A thing is really a quantum object. I have written the lower index A and the upper index A. This is just a sort of convenience of notation, because I want to say that the lower index A is a different thing from the upper index A. They don't have to be complex conjugates. They are different quantities. However, if they are complex conjugates, that's what I call a real bitwistor. So the complex bitwistors have completely independent lower A and upper A, whereas A with a lower index and A with an upper index, whereas the real bitwistors have the upper A is really the complex conjugate of the lower one. And the Z's satisfy, and W satisfy the canonical commutation rules, as we see in the middle line here. Now what I want to do here is the important thing that I want to do to the bitwistors. I consider three bitwistors, curly B, and curly C. And what I do is construct an object out of these three, which simplifies by virtue of those commutation rules. The bracketed ABC is, well, I times a sum. Now I've got a curly plus and minus and a curly arrow there. What that means, that's a notation to mean, I take the sum of all the permutations of ABC, ACB, BAC, all the 6 different permutations. When it's an odd permutation, I put a minus sign. When it's an even permutation, I put an odd sign. And that, by means of the commutation rules simplifies. I won't go into all this here, but that's how it goes through all that. If the A's and B's and C's are real, it turns out that this product is also real. But this object is, you see, because of the commutation rules and everything, it is actually another bi-twistor. You haven't any right to believe it should be if I hadn't chosen my expression appropriately. In general, if I hadn't put the curly arrow and the plus and minuses, I've done it, I would have something much more complicated than a bi-twistor, because I'd have multiplying my z's together and my w's together, and they would be more complicated things. But because of the taking the antisymmetric part, all those things turn into commutators, and the whole thing is something which, yes, I don't know, I'm jumping around here. The whole thing is something which is just an I times another bi-twistor. So that's what I'm trying to say. This triple product is another bi-twistor by virtue of the commutation rules. That's what all that's about. And it's real if the individuals are real too. Now, there's another thing I want to do too, which also is that quantum thing. I have this operator which I'm calling multiplying by I. That's the capital I operator. And you can write it down in terms of these expressions which I've got written here. The main point about it is that you can now, using the I object, you can describe a scalar product. So the third line from the bottom is A dot B, which is the scalar product, which gives you a quadratic form, which is a quadratic form with signature 4, 4. You could do all this with some proper quaternions. And these are to do with the signature 4, 4, which is the signature of twistor theory, because if you write down the real and imaginary parts of your twistors, it is indeed a quantity. The scalar product is a quantity with 4 pluses and 4 minuses. So that's what it is. And since all these things have an H cross in front of them, all these expressions which I'm talking about, I'm only considering such expressions here, I can put H cross equal to 1. So that's what I'll do from now on. Everything would have multiplied by H cross. Had I chosen H cross equal to 0, the whole algebra would have disappeared on me. So it's really a genuine thing which comes out of the quantum commutators. Now, I want to show you first how we get the Split-Octonions. The Split-Octonions, you said, noticed you had this 4-4 signature, and for many, many years I had sort of wondered whether the Split-Octonions might be sitting there in twistor theory. I'd never tried seeing that they're actually sitting there all the time, unnoticed by anybody, as far as I know. I hadn't noticed them. They're unnoticed until you have this triple product. The triple product is the thing you need, but you also need a unit element. The unit element is what you need to go from this general system to something which has the algebra of the Split-Octonions. So this unit element is chosen sort of arbitrarily, except that the coefficients E lower and E alpha have to have the property that they have scalar product of 1, which means the scalar product is 2. People worry about this, but it actually means that E dot E is 1. The bottom line you can see, but that really means that the scalar product is 2, but that's just it comes twice over because of the 2 parts. But anyway, you choose your unit element. Once you've got your unit element, then you can define any general bi-twistor, that's the curly A thing. You can define its scalar part, which is just a multiple of E, as I've written it. That's the top equation line. And then the vector part is what's left over. And the vector part is simply defined by what's left over. And that gives you something very much looks like quaternions. An algebra looks like quaternions, but it's very much like quaternions in a certain sense. Your vector part is like in quaternions, you get the expression of the top equation line there. But in the bi-twistors, your top product is simply using the triple product that I had. I could have done with taking all my I's on the outside, but I got worried about whether the sign would have been right. I can put all the capital I's in the inside, and that gives you the correct answer. So that does tell you what the vector product part is and the scalar product is, and it does give you the split-octonionic algebra. So I was quite pleased with that because it does do what I was rather hoping it would do in a kind of surprising and unexpected way. Now I want to try and talk about something else. I go back to these triple products here, and I want to think about, well, you see, let me go back to using twistors in an active way. I hope I'm getting, yes, here we are. So that was the nonlinear graviton construction. Shortly after I produced that construction, Richard Ward, who was one of my students at the time, almost at once saw how to do something else, which was to apply this to electromagnetism. Instead of using sort of the freedom of sliding your twistor space around, what you're doing here is you're taking a structure of twistor space, which is basically the sort of forms that you can write down. Normally, I haven't actually done it, but there's a form which you can write down to describe the infinity twistor. That's what gives it the, in Minkowski space, the infinity twistor is a degenerate two form. In de Sitter space, you can do the same thing with a non-degenerate two form. And these forms give you the structure that you want to preserve when you slide one piece relative to the other. So as long as that's the structure you're interested and prepared to move your parts of your twisted space around, preserving that bit, you can produce this nonlinear graviton construction. Now, what Richard Ward did was something rather similar, but a bit different, that you don't use the freedom of just the forms and stuff. You use the actual structure of twistor space, a flat twistor space, if you like. You could do it in a curved twistor space too, but in flat twistor space case, and you think of your twistor as having a phase, which is you're free to monkey with. So rather than moving your twistor around, you move the phase around. So you can slide up and down, if you like, the fiber, which gives you a twistor over the projective twistor. And that freedom is also an active thing. You can play with that, and that gives you solutions of the Maxwell equations. He generalized it later to use Yang-Mills fields and all that, but that's where you have to introduce other fields. I'm thinking of this as really playing around with twistor space itself. So you can play around with twistor space if you look at certain parts of its structure and forget the rest of the structure and manipulate the twistor space with that part of the structure. Probably you need to have a very free and flexible structure that you can move twistor space in different ways. But I don't want to move twistor space in different ways here. I want to move the bi-twistor space around in different ways. So that's really the idea. I do something like this construction, something like the Ward construction, but what am I trying to preserve now? The structure I'm going to try to preserve is the structure of this triple product. So if I try and do that, well, I should, yes, going back to the triple product, I think I have it in a minute here. Going back to this triple product, you see what it's really doing, I'm adding together with the plus and minus signs, the three bi-twistors. But because I'm doing it with the plus and minus signs, I'm really not interested in the individual A, B's, and C's construct this triple product. I'm interested in something which is the plane that's made out of A, B, and C. So if you like, it's that. See, this picture, I'm looking at it, not just the individual elements of the triple product, I mean, the object which is the triple product, which is really talking about not the individual A's and B's and C's, but the plane that they span. Also, if you like, you can consider the A's and B's and C's to be normalized, and that the objects involved have the same span. So if you move the A's and B's and C's around in that, I get an SU3. So it did strike me that is there some way of relating this to the SU3 of strong interactions? It's sort of tempting to think because it's sitting there in that triple product. Because the triple product it gives you another twistor, if you like, but you don't need to know the A's, B's, and C's individually. You just need to know that plane. And the symmetry of the objects within that plane, the thing, like in the Ward construction, you see I had a phase symmetry of the spinner, and I'm saying, look, I can play with that. So when I move around, I don't have to take in the same value for the phase as I go around. And it's the freedom I have in doing that, which gives me the cohomology that is present in the Ward construction. So I want to use the freedom in the A, B, and C to go around preserving this plane. And that freedom is the analog of the SU1 that you have in the Ward construction. So can you do something very similar with bitwistors? I have no idea because I only just thought about this last week. So it seems to me, I think it was 2 weeks ago, I can't remember, it was very, very recently. It seems to me that there is a very implicit role hiding there in twistor theory when you look at the bitwistors. So the bitwistors have this natural structure which you can use a sort of gauge freedom, and as long as you keep that rather than keeping the individual, it's like in the gauge case where you kept the twistor and you're allowed to play around with the gauge freedom in the twistor, and that gives you the Ward construction. So you're doing something very similar to that, but where now I'm considering bitwistors. Okay, I think I have to leave it there, and maybe somebody else can come up with the answer here. It seems to me there's a good chance that you can do something which really looks like the gauge freedom of SU3 in strong interactions. And if anybody can play with that and do what I think it might do, I'd be very excited to know. Thank you very much.
Well, thank you, Sir Penrose, for such a wonderful talk. We've already got some people coming up with questions here. So one very quick comment, of course, is that there certainly within the complex octonions, there is an SU3 symmetry between ladder operators, which might be very relevant for what you're talking about. But they have anti-commuting their relationships, and this is actually one of the questions I wanted to ask you anyway. Was that that when I see twistors, they look to me like they almost want to be fermionic, but in your quantization,
yes.
But this isn't the way that they're working out in your quantization. Is not a fermionic quantization. Can you kind of
there are really two questions here. Let me answer the second part first.
Okay.
Yes, all sorts of people complained about this very early in twistor theory. I remember having a long I think it was with Zumino. I went and talked to him. And certainly the string theorists were very keen and thinking there's a connection with twistor theory, and they all wanted to have anti-commuting Zs. And I said, you can't have that because the twistors, we ruin the whole subject because you can't have holomorphic functions. The holomorphic functions insist that they're real. They're not. They have commutation rules and not anti-commutation rules. Now the thing is, you see, it's really if you're talking about fermions, that obviously they've got to be anti-commuting objects, but that's when you're looking at one particle with another particle. Now these I'm only talking about within a single particle, if you like. A bitwistor space, if you like. Well, I was only talking about twistors originally. The twistor space will be associated with one individual particle. And then you can't have these things anti-commuting. But if you had another particle, then how they behave in relation to that other particle, sure, you're going to have some anti-commuting relationships. And people did play around with that. But you within the single structure with regard to the single particle, it just would wreck the subject. So you might say, why don't I do it? Well, the reason I don't do that is it would wreck the subject. I don't have a sort of physical reason, if you like, except saying that I'm working with single particle. I'm not looking at the antisymmetry, which with a fermion and a brother fermion or a sister fermion, what they would do with each other, where they would have anti-commutation rules. Sure, that's true. But if I'm talking with a single particle, I have to stick to the twistors being commutating objects. But I know people have a lot of trouble swallowing that in a way. Got used to the idea somehow that things with spinor indices have to anti-commute, or with odd numbers of spinor indices have to anti-commute. But anyway, sorry, that's my sort of grumbling answer to your.
Okay, no, that's right. No problem. So do you view them more as being bosonic then, or?
Well, you see, they're not. It's not. It doesn't apply. We're not regarding at these to do with particles. See, a twistor is not a particle. I think that's the best way to say it. Okay. If you thought of a twistor as being a particle, yes, you'd think it should be bosonic. It should be fermionic or something, but it's not. It's part of the algebra. It's part of the space, if you like. It's not. I think there is. Yeah. Why didn't I just leave it like that? It's not a particle. It's part of the description you can make of a particle, but it's not a particle.
Okay.
But
thank you.
Your other comment had to do with the complex octonions.
Yes.
So the complexified Split-Octonions, of course, are exactly the same as the complexified actual octonions. I haven't looked. I think you're referring to anti-commutations within the algebra.
Exactly, which would be should show up in your triple product.
Well, you certainly have that within the cross product, which I wrote down. So I mean, that's there. You're quite right. I mean, if you like, it's it's because the twistors have the commutation rules that you actually arise within the, I'm not quite sure how to say this, within the triple product, it's written down with an anti-commutator anyway, because you've got the minus signs in that product. So when it comes down to the analog of the cross product, which is towards the end of the talk, I was describing how you talk about the vector part of the Split-Octonions, and it is exactly quaternionic if you take the sub-algebra generated by a pair of these elements. So you need to have three of them before you start getting the non-associative property happening. But when you just have two of them, you still have the associativity. And it is just the cross product, the ordinary cross product coming in there. But when you bring in another one, you get outside that generated with two, and so you get a non. But anyway, it is that cross product which is antisymmetric. You're absolutely right. But how that ties in with fermions at that level, I'm not sure. You see, that's another question. Sorry.
No, it's okay. It actually leads. So I'll ask this very quickly, and then let other people ask questions. But it actually led into something else that I really wanted to ask you as well. Okay. So with this triple product, you motivated it by incorporating the quantum commutation relations into the triple product. And then also you have to wind up with the signature that is 4,4. But what I was curious about was that, so you built up a triple product from these things. And I was curious to know, how unique is that? Could you have chosen a different triple product that generalizes the commutation relations and have come out with a different algebra? Or could you have chosen a multiplication rule, not a triple product, but something that has more inputs, for example, and come out with something else? So I guess I'm asking about the uniqueness of.
Yes. There's probably a don't know to part of your question. All I can say is that the two things, I wanted to have something where you have something where it's a quantum object, so you get H cross outside it. So with the triple product, everything vanishes, and it's only there because of the commutation rules, because the H cross is there. And the other place was in the I operator, so the multiplying by I operator. So you need that in order to get the scalar product, so the plus, 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 minus, 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 minus. I presume you could have an analog of all that, everything I was saying, in which you try to get the actual octonions rather than the split ones. I don't know about that. I'm not sure what the answer would be to that. I mean, you certainly get the complexified octonions, of course, the same as the complexified split octonions. Yes. And you, as you say, you do get anti-commutators as part of the algebra. I don't know of any. You see, that's a challenge, if you like. I think your question is a bit of a challenge. Are there other things you can write down which would turn out to be quantum objects, so they multiply by H cross, and everything else vanishes? So you're within the algebra. But you see, the algebra I'm talking about is a quantum algebra. All the classical parts have disappeared, if you like. Everything is multiplied by H cross. So then I put H cross equal to 1. I like to say H cross and not H bar, because that's what Dirac used to say. So it isn't a bar, anyway, it's a cross.
I'll remember for next time.
Okay. I'm not going to be too dogmatic about that.
So I do.
That answer your question, yes. It may be there's more there. I don't know. The two things I hit upon were the triple product and the I operator.
Yes.
If somebody finds something else, let me know. I'd like to know. Yes.
I do have more questions, but I'll let other people go ahead with their questions. So the next person, we've got Tevian. I'll just unmute you here, Tevian. Try that one more time here. Why is it not working? There we go.
Okay, so first of all, thank you for that presentation. My question starts with a question about your SU3 symmetry. Does it preserve the split-Octonian structure?
Let me try and think if I can understand this question in this. You see, it's certainly the SU3 preserves the triple product thing, is what I'm trying to say.
So then would it not be SL3R instead of SU3?
Why there's an R there? So you mean
there's an obvious SU3 symmetry inside G2 dash, the symmetry group of the automorphism group of the split-Octonions, which would preserve the split-Octonionic product while fixing one of the split-Octonionic units.
Oh, I see. You're talking about, I'm sorry, yes, you're talking about the unit element.
Yes.
Yes, I see. Well, I wasn't yes, I don't know. You see, in a sense, I'm regarding the whole structure as being probably more fundamental than the Split-Octonions. The Split-Octonions require unit elements, but whether nature requires that in a certain sense.
Fine, but the automorphism group, of course, fixes the unit element. So
yes,
it's only
if you want a G2 star. Yes, no, absolutely right. The G2 star preserves the unit element.
And then there are subalgebras of that, or subgroups of that, would fix an additional imaginary element, and you recover real forms of SU3.
I see. Okay. I'm not sure whether that's. That's a good question.
So when you try and do grand unified theories that involve the octonions, that's where the strong symmetry tends to come out, is in an SU3 symmetry that's a subalgebra of G2.
I see. One would have to look at that. I don't know. When you're looking at string theory things, I don't know if that's what you're saying here.
Not string theory, no. But
No, okay. Okay. Yeah, well, I'm a little bit of a novice when it comes to these groups and in their connection with particle physics, because I don't know to what extent. See, I'm rather hoping that the groups that you get in particle physics, I mean, SU3, of course, is a very important one, and SU3 is a genuine gauge group, as the U1 is a genuine gauge group, because you can't break it. I mean, I could talk about colored quarks, but there is no colored quark. And the fact that the symmetry is exact allows you to do proper gauge theory with it. Whereas when you have SU2 or something, it's not really a proper gauge group. I'm a little bit confused with it in the way it's used in ordinary particle physics, because you've got your weak what do you call them? The particles, which
the gauge bosons.
Gauge bosons, yes. You see, it's as long as it's a proper gauge group. In other words, you're allowed to move it around to something. You're using the symmetry within. In my picture here, the last picture with the yellow plane, I'm imagining you can move it around so that it's rotated in SU3 around as you can produce things which have a non-trivial bundle structure, if you like. And if you break it, then it sort of spoils the picture for me. It's all right if you're using electromagnetism, because that's a genuine gauge group too. I get a bit lost when we're talking about the intellectual weak theory. So I have to think about how that might have any role here. It's worth thinking about, obviously. I don't know if I've answered your question. I'm not sure I have.
No, but I suspect there is a connection there, and I'd be very curious to work it out.
Yes. No, I think the things I'm throwing at people today is, here are things to go away and work out for me, or work out for yourself, or work out for whoever. It would be very interesting to see where it's all going.
Thank you.
And the things you're suggesting, it could well be a nice place to look, yes.
Thank you.
Okay, so John Barrett has a question. Go ahead, John.
Hi, Roger. Nice talk, thanks. I think if I can paraphrase you, that you're suggesting something like that there's some cohomology theory which constructs for you SU3 bundles with connections.
Yes, that's right.
Or that there ought to be. Perhaps we haven't, you haven't found it yet, but that's suggestion.
No, that's right. Yes. So it's
right.
very much like what the original Ward construction, which uses the internal SU1.
Right.
U1, whatever I should say. The
question
U1.
is, by linear interpolation, is there an SU2 construction that perhaps is a bit simpler?
I don't know. See, this is the one that stares you in the face. Because I needed the three terms in order to get rid of the. See, I wanted to construct something which is a genuine quantum entity using the commutation rules, which can. And I don't know. It may be related to the earlier question that maybe there is some other things for which H cross is. It only survives because of H cross. And you have another object within the system. So that's quite possible. I haven't exhausted that.
So just an ordinary product and not a triple product or something, perhaps?
Yes, there might be something else. Yeah, I mean, maybe even the multiplying by I was going, but maybe you can look at that and there's something else with just two objects. I don't know. I didn't try to think about it in an exhaustive way. I just looked at the things which I thought I needed.
Right.
Because there I was aiming for Split-Octonions, not really for particle physics. That's
yeah. Well, it'd be nice if you could produce the three groups in particle physics and nothing else.
Yes, indeed. I absolutely agree with that. Yes. Sorry, I'm going to. My screen is going to disappear on me if I don't do something quickly. my. Oh, here we go. That's it.
But you definitely need some other data. I mean, it's not that the SU3 data sitting there. There's some extra, input, some cohomology class or something which you would need to.
Well, you might need some more. Yes.
Yeah.
Oh, yeah. There could be more hiding there. These things were hiding there without being noticed for a long time, and it could be there's more hiding there. Very, very interesting to see that. Right. In fact, there could be a connection, you see, because there's when you talk about baryons and things, there's a connection between the charge, and you get these sort of quarks having fractional charge and stuff. Now, is there a connection between the SU3 here and the U1 of the Ward construction? Because it's really still there. And one might see an interplay between those two things. Is that possible? Maybe there's some structure there.
I think what you're suggesting is something like a tool for looking for the vacuum for a standard model. Because, I mean,
yes.
You're looking at solutions to the Einstein equation. So you're looking at something that solves some sort of equation. So it's not the most general configuration, but it must be something like the vacuum.
Yes. Well, there is a question unresolved. I mean, there are things about trying to solve the Einstein equations, which the things called palatial twistors. Whether this will tie in with that, I don't know. But it would be interesting to see whether the bi-twistors could lead to something. You need to. I can't quite see how to do it, because you've got to deform things in the bi-twistor space when you've got anti-commuting objects, and you've got objects which don't commute with each other.
Yeah. I must admit, I haven't seen how to do that either. So it's
So how you do that, I'm not sure.
Yeah.
Question.
Okay.
Yes.
So right.
I just think I'm throwing this out as food for thought, that maybe people can see how to combine.
So the idea is to somehow take the Ward construction and do a sort of bi-twistor version of it.
Yes. Something like that.
But people haven't done that yet. Is that the point?
Well, they haven't done it because, well, no.
No.
I mean,
that's an open problem.
Yes. I haven't done it, and I don't know who else has been working on bi-twistors.
Right. Okay. So that's a nice problem.
Yes.
So perhaps even these particle physics cases are sort of warm-up for doing that, because it's the painted on.
Yes. Yes.
It's the painted on thing rather than the deformed thing.
Yes. That's certainly a good idea.
Okay, great. Yeah, so I'll stop there.
There are various things to think about. Absolutely. No, I'd be really happy if people want to go away and think about these things and let me know if they come across something non-trivial. That would be really exciting. But yes, combining this with the actual original Ward construction, where you're looking at the phase of the twistor and therefore of the bi-twistor in some sense, would be interesting to see what you get out of it. Yeah. Also with GR, of course, but that's how that works is going to be trickier. Yes.
Great. Thanks.
Okay, so Torsten has got a question. Go ahead.
Okay, I have a similar question. At first, thanks a lot for the talk, and my question goes in the direction: what happens if you try to consider a curved B-twistor space with a triple product, something like that? I remember from your nonlinear graviton construction, you got such a Ritchie flat solution and really non-trivial things, did you expect that if you incorporate the curved version of your B-twistor space with the triple product, that maybe you got something like a coupling between the color gauge field in the sense of the Ward construction to gravity? Is it maybe possible, or is it out of reach to think about in that direction?
very interesting idea. Well, you see, it's completely. If we go back in history, the word construction can be used in conjunction with a nonlinear graviton.
Right. Yes, I know.
So
I remember.
Yes. So you could consider something analogous to that here.
Mm-hmm.
So I can't see why not.
Okay. Yeah.
It's certainly.
It must be, but maybe all these sheaf cohomology things can be then more complicated in that case too. Yeah. Okay.
Yes. Well, the trouble is it's nonlinear, probably. Whether it's nonlinear sheaves.
Right.
Nasty subjects there. Yes, that's right.
Maybe going to non-abelian cohomology. Okay. Yeah. Thanks a lot for your opinion.
Okay, so Torsten, did you have any more questions? Or no?
No. Thanks.
Okay.
They're very good questions. Thank you.
Yes. Okay, so Zurab has a question. I'm just going to try to unmute you here. Having some issues with Zoom today. There we go. Okay, Zurab, go ahead. No, I'm sorry. Try this again.
Wrong. Okay, I think it's okay now. First of all, I'd like to thank a lot for the nice talk, and I have two small questions. The octonionic product is non-associative, and that means we have natural trip product in octonionic space, which is just the associator. So my first question is, this natural trip product, whether it has something in common with the trip product you consider. And the related second question is, if with spinor construction and so octonions have something to do with space-time structure, what is geometric manifestation of non-associative? What is its geometric meaning in space-time?
Yes, well, that's related to certainly the space-time structure, the nonlinear graviton construction actually does. It's related to the earlier questions we had. When you take the nonlinear graviton construction, it does give you a curved space-time. The trouble is that it's a complex space-time, and the only real ones are the ones where the Weyl curvature vanishes, so you lose the point of the whole thing. But the hope would be that if you do something similar to bi-twistors, you could get real curved space-times. So I'm not quite sure I can remember what the first part of your question was. I mean, you could certainly hope to do something with general relativity, with curved space-times, because twistor theory certainly was probing that way back with the nonlinear gravity construction. It's just that it ran into the snag, what we call the googly problem, of only doing one helicity at a time. You couldn't combine the two. Whereas if with the bi-twistors, you automatically have the left and the right-hand parts there. So you're trying to free up the helicity from the positive frequency, if you like. The problem with the old twistor theory, in a certain sense, was that the helicity and the frequency were mixed up together. And so it gave you an asymmetry to the whole subject. Whereas with the bi-twistors, you naturally restore the symmetry. Oh, there may be some subtleties about it with signs coming in here and there. But on the whole, you've restored the left-right symmetry. I mean, one hopes there is a bit of a subtlety, because if you want to get weak interactions into it somewhere, you want to have something which does not preserve left-right symmetry. So I should imagine there probably are some subtle little signs coming in with that. It's quite possible. But it certainly connects with the curvature of space-time, at least it potentially does. if you can find an analog of the nonlinear graviton with bitwistors. But that was sort of an earlier question. But the problem here is that you have the space with its commutation rules with itself, and it's a little bit difficult to see how you construct a general perturbation or bending of the bitwistor space. But maybe there's a good way of doing it. And you can do this sort of thing with generating functions. I had an earlier article, which came out just recently, I think, yes. This was published by the Oxford University Press, is that right? An earlier article, I talk about things called palatial twistor theory, where you can imagine generating functions which would possibly do that sort of thing. But I don't know. It needs looking at.
Okay.
I mean, most of my answers here are don't knows at this point, I think.
Okay. And the first question was if the trip product you consider it is related to associator of octonions, which is natural trip product for.
Well, this is, I see. Well, my triple product
is
not that, you see, because it's the non-associativity of the octonions come about when you try to combine two of these triple products. You say, because put it like this, the triple product with a unit element, you see, your A cross B is really the triple product with the unit element as well. So the A and the B are the two elements, but you fit your unit element. Now, if you triple product with another element, with the C, you've lost your associativity because it's not it's the A unit with A and B, and then it's the product of that with the unit with the C. And that's not associative. So you can see the non-associativity coming in with the way the algebra works. Because it's not you have to put the unit element in together with the triple product that I have. And then when you take the next term, it doesn't do something symmetrical, it does something asymmetrical. So you can see why it's not associative. I don't know if that was your question here. I mean, it's sure the triple product that I write down is it's just, that's nothing non-associative about that. But the non-associativity comes in when you do that twice in an asymmetrical way.
Okay, thank you very much.
Okay, Francis, you've got a question. I'm just going to unmute you there. Go ahead.
Okay. Hello, Prof. Thank you very much for the talk. I wanted to get a little clarification from this. I noticed that with your twistors, you had the Planck's constant, the H bar, which was met. And you also did a split twistors of the octonions. But recently, some researchers have been able to use the octonions and Jordan algebras, division algebras, to show that the fine structure constants exist. They've been able to calculate that. And noticing the Planck scale, or the Planck's constant in your twistors, is there a possibility that it can also have the fine structure constants?
I'm afraid it's going to be another don't know. I don't see it coming out yet. It's conceivable. One would, of course, love to see that coming out. At the moment, I don't see any constants. It would be... I have no idea. I'm afraid of course, there is this question about whether these constants are fixed in some natural way, or is it possible to have a universe with these numbers having some other value? I rather hope that the answer is you can't have them with any other value, but that's just a religion on my part. It's not a science. I have no idea. I would rather like, certainly the fine structure constant, if it comes out of any sort of theory, would be wonderful. It does relate to a completely different lecture that I didn't give today, but it could have done, namely the CCC model, where you imagine that the universe goes through these different eons, as I call them. And then the question arises, do the constants of nature agree in the next one? And I rather hope that they don't. They do agree that they're the same. And there is a very small amount of evidence that they don't change much, at least, in this theory. But of course, that doesn't tell you very much. I know that John Wheeler, liked to have a sort of cycling universe. This was he was only using the Friedman type, closed Friedman models, where you could imagine the thing as expanding and then bouncing and collapsing again and then bouncing. And he imagined that in each of his eons, that the constants of nature would be churned up and be different in the next one. So certainly people consider such things. I rather hope, that's all I can say, is that somehow these constants are built into the theory and they have to have the values that they do for the thing to work. But I have no mathematical reason for thinking that.
Thank you.
Best I can do, I'm afraid.
Okay, I've got just a couple of very quick questions. So on the CCC model that you were talking about, the way that it's normally presented is you've got an expanding universe, which then crunches again and expands again, and it's this along one linear time direction. Could it be possible, or is there anything? I guess maybe my question is: is there anything to prevent you from having at one of the big bang times to have a forking where you end up getting two or more CC models coming out at the same time?
Well, that's a different picture. It's a bit more like Neil Turock's picture, where you've got two coming out at once. But
I see.
They're different from my scheme. Certainly, he doesn't have anything pre in the sense that I would use it. You see, the CCC model, there is a clear time direction which is preserved as you go from one year to the next. I don't see any role for a bifurcation of the universes there. It's certainly not my picture, because you want to have it a conformal manifold. Mm-hmm. See, everywhere except at the Hawking points, which are singular, everywhere else, it's a smooth conformal manifold, and so you can't bifurcate.
Right. So this is kind of what I was asking: is there something within the model that would prevent some bifurcation? And so it seems that you're saying that
the only thing that could conceivably be like that, but I don't see it happening here, would be like in the nut space. You have these very peculiar, the Taub model of the solution of the Einstein vacuum equations. And I remember Charlie Misner showed how you could get, as an evolution of that model, you could go into what was called the nut space, and you could have one right-handed or a left-handed one, I think. And you could imagine that it bifurcated and produced both at once or something. And those models, they can only do it through a very curious situation where you have a null boundary and probably has closed time-like curves and all sorts of crazy stuff. So I'm not very keen on that idea.
Okay, fair enough. I have one more very quick question, if you don't mind. In this paper that you released recently, you were talking just very briefly about compactified Minkowski space, and so this S3 cross S1. And I was just curious to know if it's how one would physically distinguish between being in real Minkowski space versus compactified.
Well, it's a bit like talking about CCC, because there you do allow yourself to get across from one infinity. Well, actually, it gets across from one infinity to the next Big Bang. So you're sort of gluing together what you might have not wanted to glue together previously, because you think you're at infinity or you're at a singularity. In the case of Minkowski's case, that's the infinity at one end being glued to another one's infinity at the other end, if you like. You have Well, you see, we don't live in Minkowski space, so I suppose that's not quite. You could consider going through de Sitter and maybe coming through the other way, not in my way. See, my way was to go through it, it would be a Big Bang. So you could imagine a collapsing universe, I suppose. You might have trouble with Gauguin indices and things. I don't know. That's just change. It flips a sign. You do have things which flip signs in a rather curious way. When you have spinor fields and so on. In compactified Minkowski space, you have a thing that I call the Gauguin index. Depending on the spin, you can put massless fields on the compactified Minkowski space, and these massless fields pick up a factor of I or of minus I. It depends on what the spin is, what the helicity is. And so that's a curiosity. Whether there's a remnant of that in these other models, I'm not sure. Quite possibly there is. That's not your question, though. I don't think.
No, it wasn't. That's right.
But you see, if you had an infinity, you see, in Minkowski space, you could imagine there's a scry, which is somehow real. But if you had just electromagnetic fields, could they get through onto another universe? Well, they can, sure. If you have a sort of great, what do you call them? Bamboo stick of these. I mean, photon fields can get through. You see, this is one thing which, if we're talking about CCC for a moment, you can get zero Rasmussen field through, which is part of the sure, gravitational signals can get through, and the claim is that they do. So that would be a question of whether you could confirm it or not in any sense, whether the scry is really there. And I guess that's sort of more your question, isn't it? Can you say that this infinite boundary to your space-time has a reality? And as far as massless fields are concerned, you could sort of consider they do, which was my way of thinking about CCC. I was worrying about these poor photons, which get to the edge of the universe and they've nowhere to go, poor things. So, oh yeah, maybe they get into, they go into the next copy of the next eon. So that's a sort of answer to your question, but not much of one, probably.
It is an answer in the context of CCC. So
okay, yeah.
Thank you. So I think I don't know if Francis has another question, or you just still have Francis, you have another question?
Hello. There's a friction
No, how do I mute you now? There we go. Oops. All right. So I think that was just he left his hand up. So does anybody else have any more questions? Oh, yes, John Barrett has another question. So I'm just going to unmute you, John. Go ahead.
Hi, Roger, you didn't mention anywhere the infinity twistor. What role does that have in this story here?
Well, I didn't mention it, partly because there's enough in the talk, as it was, and partly because I didn't talk much about gravity. But certainly in the nonlinear graviton construction, one of the thing you preserve is the infinity twistor. And you have the cosmological. That was Richard Ward too, as far as I can remember. Didn't he did that? Didn't he? I'm trying to think. Anyway, you can do it with the cosmological constant as well, as without the cosmological constant. So you can certainly do that, and that is where the infinity twistor comes into the gravitational construction. Now, it would come in with mass anyway. So if you're looking at fields with mass,
right, yes,
then you would need it. Yeah.
Yep. Okay, very good. Yes. Yeah.
But of course, the things I talked about here were where I slipped around, not having to worry too much about that. Yeah. Yes.
Okay, does anybody else have any more questions? Well, thank you sincerely, Professor Penrose, for such a wonderful talk. It's very imaginative, as always. And thank you to everybody for showing up and for your questions. I should mention that our next talk is scheduled in 2.5 weeks on Monday, the 20th of March, 6 p.m. Berlin time. We have Dr. L. Glasser from the University of Vienna speaking to us on reconstructing manifolds from truncated spectral triples. So thank you sincerely again, Professor Penrose, for such a great talk. So we hope to see everyone again next time.
Well, thanks much for the invitation and the good questions.
My pleasure. Thank you.